Hi friends, my project is the physics of spray paint. If you're going to spray paint, make sure you have a mask of some sort because there's going to be fumes. But that's it, and let's go paint. We're using cardstock paper. Make sure you're on the glossy side. The glass is what's going to allow the paint to mix. So this is what we're using for the shape of the planet. You can use anything you can find around the house. And first we're going to get a general outline of the planet. Now I'm going to add the colors. I'm going to be using blues and greens, and I'll start with darker along the bottom and it'll get brighter as I go up. So that's one coat. Now we want a second coat of colors on top of that, and that's the key. You don't want your second coat of colors to perfectly align with the first, because that's how the colors are going to blend later. So for example, my light blue should slightly cover where my dark blue was before. Now all of our colors are done, and we're going to cover the bottom half of the planet with all black and the top half of the planet with all white. So now really quickly, before that black or white gets a chance to dry, we're going to take some magazine pages crumpled up so that there's some texture on them, and we're just going to push them into the paint and pull them off so that it takes off some of the paint. So this is going to take off some of the black and white that we put on and leave behind the greens and blues. Okay, so now we're done with most of it. I'm going to leave this to dry for now. Okay, so it's been about 4 or 5 minutes, and now I'm going to cover the rest of the background with all black, and the middle part where I've put our shape, that's going to be safe from this black. And now we're going to do a little bit of highlights, and then the can is now above the paper, and I'm just pressing really lightly to get some spread out droplets which are going to look like stars. Okay, so we can take that off and we're done. There's a lot more I could have done with making the planet look more 3D or more exciting background, but I only had 2 minutes, so here's our planet. So let's talk about the forces in this can. So you saw that when I pressed the button, the paint accelerated out of the can, so that means that there must have been an unbalanced force acting on the paint. So this is a diagram of the inside of the paint can, and you can see that there's a tube that goes from the hole at the top all the way to the bottom of the can. There are 3 forces that act on this column of paint. The first one is the simplest one, which is just the gravitational force acting down. Then at the top of the tube, there's a pressure force from the atmosphere that pushes also down. At the bottom of the tube, there's a pressure force from the internal gases that pushes up. So we can use this equation, pressure equals force over area, to think about what's happening. The area of the top and bottom of the tube are the same since the tube has a constant radius. Since the area is constant, whichever side has a greater pressure will be experiencing a greater force. And the top of the tube experiences a pressure of 1 atmosphere since it's exposed to the atmosphere. The bottom of the tube is experiencing anywhere from 2 to 8 atmospheres because that's what the insides of the cans are pumped to. This means that there's a greater force acting at the bottom of the can pushing the paint up. So at least at the beginning, when there's no paint in the tube and there's no gravitational force to act down, the paint will accelerate upwards into the tube. But what happens as the paint moves into the tube? There's going to be a greater gravitational force down because there's more mass in the tube. So we can do a calculation to figure out how high this column of paint can be pushed by the pressure inside the can. So force is going to be pressure times area, but the net force exerted by the inside pressure and outside pressure is going to be delta P times the area. And we're going to set this equal to the gravitational force acting down on the column of paint, which is going to be mg. Instead of mg, we can write rho v, which is the volume density times the volume, since that's the mass. And then we can change v to a times h, because that's a volume. Now we can eliminate a from both sides and rearrange this equation to solve for h. I mentioned earlier that cans are pumped to anywhere between 2 and 8 atmospheres, so we'll use 2 atmospheres just to be conservative. In that case, our delta P would be 2 atmospheres inside the can and 1 atmosphere outside, so delta P would be 1 atmosphere, and we'll have to use our 101.325 pascals because that's a SI unit we have to use. I don't know the exact density of the paint that I'm using, but I looked at the EPA estimates for a bunch of different paints, and I think that 1100 kilograms per cubic meter is a good estimate, and that makes sense because it's slightly denser than water. So we'll plug that in and then plug 9.8 in for G, and then we'll get our answer as 9.4 meters. So this tells us that there is definitely enough pressure inside that can to get the paint up the tube because my cans are definitely less than 9.4 meters tall. Okay, so energy is another way that we can look at the paint leaving the can. So you saw from the demonstration that when I pressed the button, the paint wasn't coming out slowly and dripping and everything. It was a fast jet and you could see it hit the paper almost immediately. So that means it had a pretty large velocity. When the paint is just sitting in the can, it has no velocity. And we know that conservation of energy has to apply to this process. And we also know from the previous section that there was a net force acting on the paint in the tube going upwards, so there must have been some transfer energy here. In the previous section, we looked at pressure as force per area, but you can also look at pressure as energy per volume. And in that case, the inside of the can, which has more pressure, would have more potential energy, and the outside of the can would have less potential energy. When I press the button, there's a path between high potential energy and low potential energy. So now this potential energy is going to be converted. It's converted into two forms. One is gravitational potential energy, since the paint is moving up the tube. The other way that it's converted is into kinetic energy, because the paint goes from 0 to some non-zero velocity. So what I just said can basically be summarized by Bernoulli's equation, which is right here. And we can use this equation to estimate the velocity of the paint as it comes out of the can. So first of all, we're going to set our y equals 0 to the bottom of the can, so that when the paint is at the bottom of the can in the beginning, there is no gravitational potential energy. So we got rid of that, and we're also going to assume that when the paint is in the can, it's not moving, so there is 0 kinetic energy initially. Okay, so we'll get rid of that, and then we'll move our P2 over, so that's basically delta P again on that side, and that is going to be 2 atmospheres minus 1 atmosphere, because we will make the same estimate of the inside of the can being at 2 atmospheres, and then P1 minus P2 will give us our same number of 101,325 pascals. And then we're going to divide both sides by the volume density, which again we're going to estimate to be 1100 kilograms per cubic meter. And then for the height, I measured the can to be about 18 centimeters in height. You can see right there. Yep, and then we're gonna plug in 9.8 for G. Okay, and then we're just gonna do some quick maths and find our V is 13.44 meters per second. And I think that makes sense because that's about 30 miles per hour. So that's pretty fast, but it makes sense because you don't really see the paint moving through the air before it hits the paper. You just kind of see it appear on the paper almost immediately. So yeah, I think those two were pretty good estimates. So thank you, and hope you like my drawing.